Our objective for this project was to build a device to measure the specific weight of an unknown fluid. We wanted to take one fluid that we would know the density of, and then several unknown ones. By taking the fluid that we would know the density of off a chart, we'll be able to have a percentage error for our device. In order to construct the device, we took a slug of metal of known dimensions, 0.504 inches, 0.507 inches by 0.484 inches. So we can know the volume of this. We also know, by using calipers, the dimensions of the wood, 0.507 inches by 0.507 inches. And then we made a graduated scale on the wood so that we can know how much of the wood is submerged. We painted the wood white so that the wood would not absorb the fluid because it's porous and affect our measurements. We also took the weight of the metal using a ounce scale, and we then converted that to pounds force. We also did the same thing with the wood. These are all of our values that we need to know to calculate the specific weight of an unknown fluid.
For our project, the equation we're going to use is the Bouyance Force, that we know is the volume submerged times the specific weight of the fluid. In this side, we have the free body diagram where we know that the weight of the metal, the weight of the wood, and the buoyancy force going up. Since we know that our device is going to be on a static equilibrium, we know that the summation of the forces in the y direction is going to be equal to 0. In this case, we have the buoyancy force going up minus the weight of the wood and weight of the metal because they are going down. After some algebra, we end up with this equation, which is the specific weight of the fluid, where we know the total weight of our device is equal to 0.088 pound forces. And here we have the summation of the volume of the metal and the wood. In this case, we have that this is our number for the volume of the metal, since we know it's going to be underwater, plus in here we have the cross-section area of the wood times the height, which is unknown. It will depend on the specific weight of our fluid. And here we have the conversion from inches cubed to feet cubed.
For our first trial, we're going to measure the specific weight of distilled water. We're going to see how far the hydrometer sinks before it reaches static equilibrium. Eight and 15/16 inches.
In this case, we have sugar water, where we use distilled water. We added 3 cups of sugar. We let it rest, and now we're going to use our device to measure the height in this fluid. The number is
8 and 11/16 inches. For our third trial, again, we had 3 cups of water. With this time, we added 1/4 cup of salt, iodized salt.
Wow.
8 and 3/16 of an inch. All right, for our fourth trial, we pulled some water out of the contraband bayou through campus. We're gonna see what the density of that is. We don't know what the composition of it is. Nine inches.
Here we have a result section. We can see all the values for the specific weight for each fluid that we have at the beginning. The still water was 62.79 pound-force over feet cube. If we compare that to sugar water is just a little bit higher than this value. Even if we see salt water, we can notice that it has a higher density than the distilled water and sugar water. It has a 68.22 pounds-force over feet cube, which makes it heavier. In here, river water, we found that it was a little bit lower than the distilled water, probably because it was outside, it was hot outside. We have a value closer to the 62.4, which is the theoretical value, but these are our results.
So in conclusion, we ended up with actually a pretty accurate hydrometer here. We calculated our percent error based on known value, which we know for distilled water, and we ended up with 0.58% error. Where that comes from is probably there's a little bit of variation in the thickness of the paint on this, which leads to slightly different cross-sectional areas going up the wood. There's probably also not cut quite exactly 100% square, so our volumes probably have a slight error to them. And then just our scale is not exact, which probably is a big part of it too.